In the Geophysics Department at GFZ Potsdam, the German National Center for Geosciences Research, we cover a wide range of geophysical observations which aim to study the dynamic behavior of the solid Earth. We also stretch our research to magnetospheric physics in order to include solar winds and radiation. We have no direct window into the interior of the Earth. Therefore, we study with geophysics the interior of the Earth indirectly from Earth's surface or from space to provide further evidence of the geodynamic behavior of the solid Earth. In addition to the research-related objectives that we pursue, for instance, global tectonics, geohazards or georesources-related research, we also provide different community services. These encompass the provision of the Geomagnetic Index, internationally operating geophysical instrument pool in Potsdam, GIP, and it also includes the Geophone network that delivers rapid earthquake responses.
GFZ built the Geophone system to observe earthquake activity worldwide, and it consists of 90 seismic stations which operate in all kinds of environments, from polar regions to jungles to deserts. And each of these stations can record minute ground motions so that it's sensitive to earthquakes on the other side of the planet. And we combine the data from all these stations to find where earthquakes happen. We're able to do this within a few minutes of the earthquakes happening anywhere in the world for moderate and large earthquakes. Seismology is a cooperative science. We rely on the hosts of our stations to look after them together with us. And only by combining data sets from many networks we are able to observe seismic ruptures in detail, find crisp images of basically in real time. Many earthquake centers and tsunami warning centers worldwide make use of this facility for their warning procedures. The Alps are a spectacular place to study mountain building, as they're still actively evolving today due to the northward push of Africa into Eurasia. And in Alpbray, 18 European countries came together to operate a very dense network across the Alps and also the surrounding regions, and to be able to image the structure beneath the Alps in great detail. GFZ's contribution is to build an even denser network across a particular place in the Alps that is very enigmatic, because there it seems that the polarity of subduction is changing direction. We have teamed up with our partner institutes in Italy and Austria to put stations at 15-kilometer distance. So with this dense network we will reach a level of resolution that we are able to link faults at the surface to the deformation in the upper mantle and lower crust. There is a huge gap still in our networks in the oceans, because dedicated undersea cables are just incredibly expensive to maintain. But there are hundreds of thousands of kilometers of communication cables already present, which are currently completely unused for this purpose, but offering access to communication and to power. We are currently engaged in discussions with operators of these cables and equipment manufacturers to see if we can add sensors to these cables and therefore allow observation also on the seafloor.
I am the leader of the Helmholtz group Crystals, which is embedded in the GFZ's geodynamic modeling section. In that section we model large-scale geodynamic processes like mantle convection and plumes, but also rifting and subduction and earthquake cycles and tsunamis. In my group we focus on continental rifts and rifted margins, and we combine numerical simulations with available geological and geophysical datasets. To this aim we work with groups at GFZ and the University of Potsdam, and of course with international collaborations, for instance from Australia, Italy and the US. In future we will also look at the largest rift system, the East African one, and we will answer questions like how do tectonic processes interact with migration of volatiles and melts. The increasing power of supercomputers will help us answering these questions, because it will allow 3D high-resolution numerical modeling across the scales. Measurements have shown that rifts release large amounts of CO2 because they connect the huge carbon reservoir in Earth's mantle to the surface and to the atmosphere. We analyzed the extent of rift systems since the breakup of Pangaea during the last 200 million years, and we found that the global rift length evolution matches the CO2 history of the atmosphere. This shows that tectonic processes are not only responsible for shaping our continents, but also have strong impact on long-term climate changes.
The Earth magnetic field is generated in the outer core due to moving liquid iron, and it reaches out several Earth radii into space, where it protects us from solar and cosmic particle radiation. Some of these particles are trapped in the magnetosphere and form the Van Allen radiation belt. This is a region which is dangerous to satellites, which we depend on in our daily life. We at GFZ want to understand the evolution of the geomagnetic field in short and long time scales, and we lie special focus on the ionosphere and sources in the magnetosphere to best quantify the state of the space environment. This space environment is very harmful to satellites our society is relying on, and it is also responsible for interruptions in trans-ionospheric emissions like GPS.
The Russian authorities operate a real-time seismological monitoring system with stations at different volcanoes in Kamchatka. But to investigate the detailed structure of a volcanic system and the processes in its interior requires dedicated experiments with many stations focused in a smaller region. To investigate the Geophysical volcanic group, the GFZ, together with French and Russian partners, conducted a field experiment and installed 83 temporary seismic stations around the 4,700 meter high Mount Geophysical. The Geophysical volcanic group comprises 13 volcanoes and is one of the most active places in the world. To access these sites with 40 kilograms of equipment per station, we had basically only one option: to use a helicopter. With drones, we bridge a gap between surface and remote sensing observations with satellites. One speciality is to go close to the summit of an erupting volcano independently of scheduled satellite flights and without risking lives. The precise deformation and temperature measurements reveal precursors and dynamics that has been completely undiscovered a few years ago.
We have sinkhole recognition program. Sinkholes are circular to elliptic structures at Earth's surface, which can lead to collapse if soluble rocks in the subsurface bring out cavities, and these cavities collapse if the strength of the overburden is mechanically not any longer stable. This may pose a severe hazard, especially in urban areas. And to study this, we want to look at precursor phenomena, to study if there are interactions of processes that we can depict easily and understand, and if there are small variations that we can feed in those systems for early recognition. To summarize the future research goals, firstly, we would like to use the full observational potential that we have to close the gap between surface and deeper Earth observations. This may help geodynamic studies, but also resources-related questions. Secondly, we would like to include magnetospheric physics. This will help broadening our geohazard spectrum towards space weather. And then thirdly, we may count on geohazards, which means to deliver rapid responses, hazard maps and also risk dynamics to give some decision potential for preparedness and early warning.